Let's start to talk now about mechanical forces on dislocation. So we've talked about stress fields of dislocations, but typically we're going to be applying stress, and those stresses are going to act on dislocations in our materials. So let's look at our, we're going to apply in this system a negative actually, sigma 3,1, at least drawn in this figure, and we are going to create a force on our screw dislocation. So you can see the screw dislocation nucleates, grows, leaves a step behind. This is slip type motion. It's always going to be parallel to the Burgers vector. But anyways, the work that's done on this system is stress, so force per unit area times a distance. That is an energy value. But we want to write this in terms of a force per unit length of our dislocation. So we could define a value F, and you can see that definition here. You could also rewrite it F in terms of sigma 3,1 over times B. And that is our force per length of our dislocation. You can basically define it as such. So we want to look at what is the actual force on our dislocation as it moves through our material. So we are going to find some differential element, dA, and it is going to be described as you see here, dA. It is our tangent vector crossed with this EDS value here. The work that's going to be done, it's going to be minus B. We're going to dot it with that area as it moves essentially through that material. So that's, again, our work function. You can see that right here. Let's just define that. That's our work function. And we can define our force in terms of work. Again, that's going to be the work that's done over some distance ds. And we can define, finally, our Peach-Koehler force, a pK force. So our pK force is our stress tensor, our 3x3 stress tensor. Usually, again, that's the stress applied. Oh, something's going on. All right. Hopefully this is working now. 3x3 stress tensor. We're just going to define it out. So it is that whole 3x3 stress tensor, which is a second-rank tensor property. So 6 components due to stress values here. And we're going to dot that with our 3x1 Burgers vector in 3 dimensions, 1, 2, 3, whatever those values tend to be. And we're going to cross that result with our tangent vector. And that will give us our pK force. And force is going to be a first-rank tensor property, and it's going to have some direction. So it'll have a force that will move that dislocation in one of our 3 directions. Or some component that tries to make it move, or stress the force that's at those different directions. So this is really this is a multi-scale approach. We're taking a force that acts on an atomistic length scale, and we are basically scaling it up to a macroscopic. This multi-length scale approach is very characteristic of material science. So this is going to be characteristics of dislocation glide. So it's going to be resulting in slip motion, slipping along slip planes. Now this is where we connect all the way back. Slip planes will typically be on close packed planes. Slip directions will be typically in close packed directions as well. Anyways, but we will get into that much more a little bit later. And that will be, again, dislocation. That is distinct from dislocation climb, which is a thermally activated. It's a diffusive process. So when you're applying a force, that is going to move via glide. If you are thermally activating it, that's going to be from climb. So we can actually now start to play around and calculate these forces, or these pK forces here. So let me actually pull up another notebook right here. So we have our general stress tensor. So we have our screw T, our edge T, our Burgers vector for screw and dislocation. And if we cross this, I can see the different components that lead to glide for my screw. I could also see the components of stress that actually lead to glide for my edge dislocation as well.